Hello everybody. In this video I want to talk about how to describe lines in R3. So we're probably all familiar from our basic middle school math class how to do lines in the plane, y equals mx plus b, point slope form, all of these things. Well, in R3 it's really pretty similar. But let's just get rolling on it. So there's two ways that are equivalent to each other that we want to be able to formulate the equation for a line. So we're going to be looking at the parametric equations and symmetric equations for a line. Okay. So the whole idea here is we want to be using like a parameter to express how x, y, and z are all moving together. So this is a little bit different and a little bit tricky, but basically our line is going to be a function of some parameter. We're going to call it t. And this is going to be just the set of all x, y, and z such that x is equal to x as the parameter changes, y is equal to y as the parameter changes, and z is equal to z as the parameter changes, where our parameter, since the line is infinite in all directions, our t is going to be in negative infinity to infinity. So this might seem sort of confusing, but it's really not. Okay, so to describe a line, we just need a point on the line and what direction the line is going in. So we'll just call this a direction vector. Okay, so let's just do a simple example and we'll see how we get the parametric and symmetric equations. So let's let the point, for simplicity, just be the origin. And we'll let the direction be 1, 1, 1. So if you imagine this is positive x, positive y, and positive z. Our starting point for the line is the origin, and then we're going to move, for each unit we move in x, we're going to move 1 unit in y and 1 unit in z. So our line in R3 is just going to be sort of an extension of this thing in both directions. Sorry, this is like the world's worst looking line, but it's like, it's this thing. Ooh, that's really bad. Sorry, everyone. Okay, so how are we gonna do this? The basic thing that you need to know is this position vector equation is just the point you start with. This is like analogous to point slope form in the plane. So it's going to be 0, 0, 0 plus our parameter t multiplied by the direction that the thing goes in, that the line goes in. So as you can see, if we let t vary from anywhere from negative infinity to infinity, let's say t was 10, you'd get the point 0, 0, 0 plus 10, 10, 10, which is this point 10, 10, 10, like somewhere up here. 10, 10, 10 is on the line. And this checks out for any value of t that you plug in. So this is the essence of parameterization, which is that you've got a number of different variables, in this case 3 variables, that are all changing in a predictable way based on a third variable, in this case t. So x, y, and z are changing as functions of t. Okay, so to complete our picture of like how to describe this line, we would just say that the line is equal to the set of all points x, y, and z, such that x equals, well, 1 times t is t, y equals t, and z equals t. And we're letting t vary from from negative infinity to infinity. And that's it. Okay, so if somebody said to you, write the parametric equations for this line, what they would want is to see this bit here. And that pretty much says it. You just write that x of t equals t, y of t equals t, z of t equals t. And you'd be done. These are the parametric equations. Check. Good. Okay, so how do we write the symmetric equations? Well, in general, what we would do is we would take the parametric equations and solve for t and just set them equal to each other. So in this case, the symmetric equations are just x equals y equals z. And that's it. Done. Okay, so now what we want to do is we want to see a more complex example, or something where the line isn't just intersecting all 3 planes at the origin, and see sort of how that looks. So over here for example 2, our point is going to be, let's say 2, -1, 3, and the direction can just be, let's say, -5, 3, 8. So you might look at this and think it's pretty intense. We've got a point that's going to be at 1, 2, -1, and 3. So here's our point. And then x is going to move -5, y is going to move 3, and z is going to move 8. So it's like some kind of crazy line up here. Okay, so we want to describe this line using both, or we want to see how it looks in parametric and symmetric form, and then I also want to find out where does it intersect. And just for simplicity, we'll let it be the xy plane, but you'll see that it's very easy once you know how to do that, how you could ask about it intersecting any plane, any coordinate plane. In terms of intersecting an arbitrary plane, that's the kind of stuff that we're going to get to in future videos. But okay, so let's get these symmetric equations. The parametric equations are easy to get. X as a function of our parameter t is just going to be equal to 2 minus 5t. Y as a function of t is going to be equal to -1 plus 3t. And z as a function of t is going to be equal to 3 plus 8t. Okay, there's our parametric equations. Check. Symmetric equations, well, on the fly, it's not that hard even to just do this on the fly. We just solve each of these for t. So it would be x minus 2 over minus 5 is equal to t. We know that we can solve y for t as well and get y plus 1 divided by 3, and that's going to be equal to z minus 3 over 8. Symmetric equations. Check. Good. Now, a really cool thing to note here is once you're staring at the symmetric equations, you can read off the point on the line. So in this case, you would just say, you can see that it's 2 minus 1, 3. And you can also read off the direction as minus 5, 3, 8. So it's just going to be x minus whatever the point is in x, y minus, then negative 1. You can see how that follows. Okay, so the question is, where does this thing hit the xy plane? Well, look, at the xy plane, clearly z equals 0. Okay, well, if z is equal to 0, we can solve this equation right here for t. So what you would get is that z is 0, so you would get minus 3 over 8. So t, this implies that t is equal to minus 3/8. Okay, and then you would just go in and solve for x and y using the value of our parameter. Okay, so x is going to be equal to 2 minus 5 times negative 3/8. Okay, and we've got that y is equal to minus 1 plus 3 times negative 3/8. Okay, so this doesn't look so clean, but let's just do it and see what we get. We would get 2 minus, okay, 5 times minus 3 is minus 15. Eighths. Okay, so 2, we could just call that 16/8. Okay, so 16 plus 15 is going to be 31 divided by 8, which is very close to 4. Okay, and then for y, we've got, let's see, we've got minus 1. 3 times minus 3 is minus 9 over 8. Minus 1 could be minus 8/8. Okay, so we've got minus 8 minus 9 is minus 17, minus 17/8. And that's like pretty darn close to minus 2. Okay, so the point of intersection, I just made these approximations that we can check to see if what we got is reasonable. So we want to get something that's like 4 minus 2, 0 as our actual point of intersection. Give some big approximately's here. And we go over into our picture. We remember that, where did this guy come from? We know he was over here, so let's say we had 1, 2, 3, 4, 1, 2, and 0. So my claim is that this line is going to hit the xy plane like somewhere here-ish. And, you know, based on my picture, that seems to be somewhat reasonable. All right, hope everyone has enjoyed, and let's all go ahead and have